Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. The universe whispers its secrets through light, radiation, and particles that have journeyed across vast expanses of space and time. Today we stand at a unique vantage point, peering into both the past and future of our cosmos to answer a profound question. Are we inhabiting a youthful universe just beginning its story, or one that's slowly marching toward its inevitable end? To understand our place in cosmic history, we must first grapple with the immense scales involved. When astronomers study the observable universe, they're examining a sphere approximately 93 billion light-years in diameter. This means the light from the most distant objects we can detect has been traveling for nearly 14 billion years. The JWST, James Webb Space Telescope, continues to push these boundaries, revealing galaxies from when the universe was a mere 300 million years old, a cosmic infant by any measure. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The cosmic calendar provides a useful metaphor. If we compress the entire 14 billion-year history of the universe into a single Earth year, modern humans would appear only in the last minute of December 31st. Our recorded history occupies merely the final seconds. This perspective suggests we're latecomers to a universe well into its existence, yet time is relative, and cosmological timescales dwarf human understanding. To properly assess whether our universe is young or old, we need metrics beyond simple chronology. Astronomers examine several key indicators: the rate of star formation throughout cosmic history, the predicted lifespans of various stellar classes, the cycling of elements through generations of stars, and the universe's expansion dynamics. Current data from observatories like the HST, Hubble Space Telescope, indicates that star formation peaked approximately 10 billion years ago during Horns, what astronomers call cosmic noon. During this period, the universe was producing stars at rates tens of times higher than today. By comparison, our current epoch shows a dramatic decline in stellar nurseries. Galaxies like our Milky Way continue forming stars, but at much reduced rates compared to their earlier activity. Element abundances tell a similar story. The very first stars formed from primordial hydrogen and helium, the simplest elements created during the Big Bang. These massive, short-lived stars forged heavier elements in their cores and scattered them through space when they exploded as supernovae. Each subsequent generation of stars incorporated these metals, gradually enriching the interstellar medium. Today's stars, including our Sun, contain significant quantities of elements like carbon, oxygen, and iron, evidence of multiple generations of stellar processing. The universe's dark, energy-driven expansion adds another dimension to this timeline. As space stretches, galaxies move farther apart, and the cosmos becomes increasingly diffuse. Over hundreds of billions of years, this expansion will isolate galaxy clusters into island universes, each ultimately unreachable from the others. This inevitable spreading suggests a universe transitioning from its formative era toward a prolonged period of isolation and dissipation. As we close this first exploration, we recognize that answering our question requires balancing multiple timescales: the age of the universe against its expected lifetime, human existence against cosmic evolution, and the past productivity of the cosmos against its future potential. In the next section, we'll examine the universe's earliest moments to establish a foundation for our cosmic timeline. The story of our universe begins with the Big Bang, not an explosion in space, but an expansion of space itself. Approximately 13.8 billion years ago, all matter, energy, space, and time emerged from a state of extraordinary density and temperature. In less than a microsecond, the universe expanded exponentially during a phase called inflation, growing from subatomic scales to astronomical ones. This earliest epoch remains largely theoretical, as no direct observations exist from before the cosmic microwave background radiation, CMB. The afterglow of the Big Bang, detected by missions like NASA's Cosmic Background Explorer, COBE, and the European Space Agency's Planck Observatory. This radiation dates to approximately 380,000 years after the Big Bang, when the universe finally cooled enough for atoms to form and light to travel freely. After the CMB's release came a period cosmologists call the Cosmic Dark Ages, a time before stars or galaxies existed, when the universe consisted primarily of neutral hydrogen and helium gas clouds slowly condensing under gravity's influence. This dark period lasted for hundreds of millions of years until the first luminous objects formed. Recent observations from the JWST have revolutionized our understanding of this first dawn of light. The telescope has detected galaxies, like JD's GSZ 13-0, that appear to have formed just 300 million years after the Big Bang, far earlier than previously thought possible. These primitive galaxies were small by modern standards, but intensely active in forming stars. They began the process of reionization, where ultraviolet radiation from the first stars stripped electrons from the neutral hydrogen permeating space, making the universe transparent to most wavelengths of light. By 1 billion years after the Big Bang, reionization was largely complete, and galaxy formation had accelerated dramatically. What followed was a period of remarkable cosmic fertility, lasting billions of years. During this time, galaxies collided and merged frequently, triggering intense bursts of star formation. Supermassive black holes at galactic centers devoured surrounding matter, shining brilliantly as quasars, some of the most luminous objects in the universe. The peak of this activity, cosmic noon, occurred when the universe was approximately 3 to 4 billion years old. During this golden age, star formation rates across the cosmos were up to 10 times higher than those observed today. Massive galaxies assembled their bulk during this period, with the Milky Way acquiring much of its stellar population. The universe was more compact then, with galaxies clustered closer together, making interactions common and spectacular. From this perspective, we see that the universe experienced its most productive and energetic period in what might be considered its adolescence. Today, at nearly 14 billion years old, the cosmos shows signs of maturation. Star formation has declined across most galaxies. Galaxy mergers occur less frequently due to cosmic expansion, and the largest structures in the universe, galaxy clusters and superclusters, have largely stabilized. This transition from a period of intense activity to one of relative quiescence might suggest a universe past its prime. However, cosmic scales demand we consider longer timeframes. Main sequence stars like our Sun live for billions of years, while red dwarf stars, the most common stellar type in the universe, can shine for trillions of years. The smallest of these stars, born in the universe's youth, have barely consumed 1% of their hydrogen fuel. As we contemplate this timeline, we begin to appreciate the perspective problem in judging the universe's age. In human terms, 14 billion years sounds ancient, but when measured against the potential future of the cosmos, we may be witnessing just the opening chapters of a much longer story. In the next section, we'll examine the current state of the universe to better assess its position on the cosmic timeline. The stars serve as cosmic timepieces, their life cycles providing crucial insights into the universe's progression. Every star we observe represents a point on an evolutionary continuum, from the nuclear fusion-powered main sequence to various end states including white dwarfs, neutron stars, and black holes. By examining stellar populations across galaxies, astronomers can determine whether we inhabit a universe still in its productive prime or one sliding towards senescence. Stars form when dense regions of molecular clouds collapse under their own gravity, heating until nuclear fusion ignites in their cores. This process continues throughout the universe today, though at diminished rates compared to earlier epochs. The Orion Nebula, located approximately 1,400 light-years from Earth, offers a glimpse of this ongoing creation, with hundreds of stars forming within its dusty confines. Similarly, the Eagle Nebula, famous for its pillars of creation photographed by the HST, shows star formation continuing in our galactic neighborhood. However, observations across multiple wavelengths reveal that peak star formation occurred when the universe was approximately 3 billion years old, roughly 22% of its current age. During this period, the average galaxy produced stars at rates 10 to 100 times greater than observed today. The ALMA, Atacama Large Millimeter Array, telescope, has detected galaxies from this era forming thousands of solar masses worth of stars annually, compared to the Milky Way's modest rate of about 1 to 2 solar masses per year. This decline in star formation represents a fundamental shift in cosmic productivity. Several factors contribute to this slowdown: the gradual consumption of available gas, the heating and dispersion of remaining gas by stellar feedback, and the increasing influence of supermassive black holes at galactic centers, which can expel gas through powerful outflows. Additionally, as the universe expands, galaxies become more isolated, reducing the merger events that might otherwise trigger intense bursts of star formation. The processing of elements through stellar generations provides another metric for cosmic age. Early stars consisted almost entirely of hydrogen and helium. Each generation enriched the interstellar medium with heavier elements created through nuclear fusion and explosive stellar deaths. Today's interstellar medium contains significant quantities of these metals. Astronomers use this term for all elements heavier than helium, indicating multiple cycles of stellar birth and death. The metal content of stars, their metallicity, increases with each generation. Our Sun, with approximately 2% heavy elements, represents a third-generation star. Its composition includes atoms forged in long-vanished stars that lived and died before our solar system formed 4.6 billion years ago. This elemental enrichment took time, suggesting again that we inhabit a mature cosmic environment. The most massive stars, those exceeding 20 solar masses, live brief lives measured in millions rather than billions of years. They're violent. Deaths as supernova have helped seed the universe with heavy elements. The declining rate of these explosions, as tracked by wide-field surveys like the Zwicky Transient Facility, further suggests a universe past its most active phase of element production. Yet this narrative becomes more nuanced when we consider red dwarf stars, which comprise approximately 75% of all stars in the Milky Way. These low-mass stars burn their hydrogen extremely slowly and can remain on the main sequence for up to 10 trillion years. The oldest red dwarfs, formed in the universe's first billion years, have completed less than 1% of their potential lifespans. From their perspective, the universe remains in its infancy. This dichotomy between a universe whose most dramatic stellar events have tapered off and one whose most numerous stars have barely begun their lives complicates our assessment. Are we witnessing a universe that has peaked in productivity, or one whose slower but more sustained processes have only just begun? The answer may depend on whether we value intensity or longevity as the more significant measure of cosmic vitality. In 1998, two independent teams of astronomers made a discovery that fundamentally altered our understanding of cosmic destiny. Studying distant Type Ia supernovae, stellar explosions that serve as standard candles due to their consistent brightness, these scientists expected to find the universe's expansion slowing due to gravity. Instead, they discovered something astounding. The expansion was accelerating. This unexpected finding earned Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011. The culprit behind this acceleration appears to be dark energy, a mysterious repulsive force that comprises approximately 68% of the universe's energy content. Unlike gravity, which weakens with distance, dark energy's influence grows as space expands, causing galaxies to recede from each other at ever-increasing speeds. This acceleration presents a critical juncture in our quest to determine the universe's life stage. If dark energy remains constant, as current measurements suggest, the universe faces a bleak, protracted future known as the Big Freeze or heat death. In this scenario, galaxies beyond our local group will eventually accelerate beyond our cosmic horizon, becoming permanently unobservable. Stars will exhaust their nuclear fuel, galaxies will grow dark, and black holes will slowly evaporate through Hawking radiation over unfathomably long timescales, measured not in billions, but in trillions upon trillions of years. Given this potential, our current era, 14 billion years after the Big Bang, might represent just the opening moments of cosmic history. Compared to the universe's projected lifespan, we inhabit what might be considered its earliest youth. The universe could remain dynamic for 100 trillion years as stars continue forming, albeit at decreasing rates. Even after star formation ceases, existing stars will shine for trillions more years before the universe enters its long dark senescence. However, dark energy remains poorly understood. The lambda CDM model, our current standard model of cosmology, incorporates dark energy as a cosmological constant, unchanging throughout space and time. But theoretical physicists have proposed alternative models where dark energy's properties might evolve. If dark energy were to strengthen substantially over time, a scenario called the Big Rip, cosmic acceleration could become so extreme that it would tear apart galaxies, solar systems, planets, and eventually atoms themselves, bringing the universe to a premature end. Alternatively, if dark energy weakened or reversed its effect, the universe might eventually stop expanding and begin contracting, leading to a big crunch, where all matter collapses back into a singularity, potentially triggering another Big Bang in a cyclical cosmos. These scenarios would suggest we inhabit a universe much closer to its end than its beginning. Current observations from missions like the Dark Energy Survey and the European Space Agency's Euclid telescope aim to constrain dark energy's properties by mapping the universe's expansion history with unprecedented precision. Preliminary results support the cosmological constant model, suggesting the Big Freeze remains the most likely outcome. The dark energy dilemma illustrates how profoundly our cosmic perspective depends on future evolution. If the universe continues, accelerating indefinitely, then relative to its total lifespan, human civilization has emerged remarkably early, within the first 0.01% of cosmic history. We would be witnessing the universe's brief fertile period before its long descent into darkness. This timing seems suspiciously fortunate, leading some cosmologists to invoke the anthropic principle, the idea that our observations are necessarily biased by the conditions required for observers to exist. Stars and habitable planets cannot form indefinitely in an expanding universe. If intelligent life requires stars, then observers like us must evolve during the universe's stellar era, regardless of how brief this window might be compared to. Cosmic timescales. As we contemplate our place in this accelerating cosmos, we face a paradox. We appear to inhabit an ancient universe by human standards, yet a remarkably young one relative to its potential future. The dark energy driving cosmic acceleration creates a universe with a brief, vibrant youth, followed by an extended quiet dotage, and we find ourselves witnessing the transition between these phases. Among the universe's most enigmatic objects, black holes serve as both timekeepers and destiny shapers in our cosmic narrative. These regions, where gravity dominates all other forces, mark the end point for matter in many cosmic systems, from massive stars to entire galactic cores. The universe currently hosts billions of these objects, from stellar mass black holes weighing several times our Sun to supermassive behemoths, millions or billions of solar masses found at galactic centers. The Event Horizon Telescope's groundbreaking 2019 image of the black hole at the center of galaxy M87 and subsequent imaging of Sagittarius A star at the Milky Way's heart confirmed what theory had long predicted. These cosmic singularities are surrounded by event horizons beyond which nothing, not even light, escapes, or so it appeared, until Stephen Hawking's revolutionary work in the 1970s. Hawking demonstrated that quantum effects near black hole horizons cause these objects to emit radiation and gradually lose mass. This process, known as Hawking radiation, proceeds excruciatingly slowly for large black holes. A black hole with the Sun's mass would take approximately 10 to the power of 67 years to evaporate completely, many trillions of times longer than the current age of the universe. This timescale reveals something profound about our cosmic position. Even the oldest black holes formed in the early universe have lost only an infinitesimal fraction of their mass through Hawking radiation. From this perspective, we inhabit an extremely young universe, one where black hole evaporation, which will dominate the far future universe, has barely begun. The fate of information that falls into black holes represents one of physics' greatest, unresolved paradoxes. Quantum mechanics dictates that information cannot be destroyed, yet anything crossing a black hole's event horizon appears permanently lost. Theoretical solutions like holographic correspondence suggest information might be preserved in subtle quantum correlations in the Hawking radiation, but definitive answers remain elusive. This information paradox highlights another aspect of our cosmic timing. We exist in an era when these fundamental questions remain approachable through observation. As the universe continues expanding, galaxies beyond our local group will eventually become unreachable and ultimately unobservable. Future civilizations emerging in the distant cosmic future would find themselves in isolated island galaxies, unable to observe enough of the universe to reconstruct its history or verify cosmological theories. Black holes also shape galaxy evolution through feedback processes. As matter falls towards supermassive black holes at galactic centers, it forms accretion disks that release enormous energy. This energy can heat surrounding gas, preventing it from cooling and forming stars, effectively regulating galactic growth. Observations with X-ray telescopes like NASA's Chandra Observatory reveal that such feedback has intensified over cosmic history as black holes have grown larger. The relationship between galaxies and their central black holes appears finely tuned, with black hole masses typically proportional to their host galaxies' central bulge masses. This correlation, discovered in the 1990s, suggests black holes and galaxies evolved together, each influencing the other's development. Modern galaxies like the Milky Way show signs of having reached an equilibrium state, where black hole feedback has established a balanced ecosystem that allows for continued but moderated star formation. This maturation process implies we inhabit a universe that has progressed significantly from its tumultuous youth but hasn't yet approached the sterility of extreme age. Galaxies continue forming stars, albeit more slowly than before. Black holes continue growing, though at reduced rates compared to the quasar era billions of years ago. Matter continues organizing into increasingly complex structures, enabling phenomena like life to emerge. From the perspective of black hole, physics and information theory, we find ourselves at a privileged moment, late enough for supermassive black holes to have formed and shaped galactic evolution, but early enough that the universe remains observable, dynamic, and comprehensible. The major chapters of cosmic structure formation have concluded, but the epilogue of universal heat death remains inconceivably distant. This middle position, neither witnessing the universe's explosive beginnings nor its quiet ending, offers unique opportunities and challenges for cosmic understanding. We have arrived late enough to reconstruct the past, but early enough to project the future, standing at what might be considered cosmic adulthood, a universe that has developed its phage structures but remains vibrant and active. When contemplating our universe's age, we must consider not only the lifespans of stars and galaxies, but also the emergence of complexity, particularly life. Earth's biological story stretches back approximately 3.8 billion years, developing from single-celled organisms to the rich biodiversity we observe today. This evolutionary journey has unfolded over roughly 27% of cosmic history, a substantial fraction that suggests biological complexity requires significant time to develop. Yet, viewed against the potential future of habitable environments, life as we know it may be just beginning. Red dwarf stars like Proxima Centauri can remain on the main sequence for up to 10 trillion years, potentially supporting habitable planets for periods hundreds of times longer than our sun's entire lifespan. If life can adapt to the unique challenges these star systems present, such as intense stellar flares and tidal locking, the universe's biologically productive era might extend far beyond our solar system's habitability. The universe is changing. Chemical composition also contextualizes life's emergence. Carbon, oxygen, nitrogen, phosphorus and other elements essential for Earth-like biochemistry were scarce in the early universe, produced gradually through nucleosynthesis in successive stellar generations. Planets forming in the first billion years after the Big Bang would have contained significantly fewer heavy elements than those forming today. Metallicity studies of exoplanet systems support this evolution, showing that stars richer in heavy elements are more likely to host planets, particularly gas giants. This suggests that conditions for complex life have improved over cosmic history, with Earth-like planets becoming increasingly common as the universe enriched itself with biologically relevant elements. The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of active, communicative extraterrestrial civilizations in our galaxy. The equation incorporates factors including star formation rates, the fraction of stars with planets, the fraction of those planets that could support life, and the likelihood of intelligence evolving. When astronomers apply current exoplanet statistics and conservative biological assumptions to this equation, they typically arrive at estimates suggesting intelligent life should be widespread across the galaxy. This prediction creates the famous Fermi Paradox. If intelligent life should be common, why haven't we detected it? One compelling resolution involves cosmic timing. If technological civilizations typically emerge after roughly 10 billion years of stellar and planetary evolution, as happened on Earth, then humanity may represent one of the first waves of intelligent life in our galaxy. We might not be alone, but we could be among the early arrivals at the cosmic evolutionary party. This perspective aligns with astrobiological models, suggesting that Earth-like planets orbiting Sun-like stars represent a relatively early expression of habitable environments. As the universe continues aging, planets orbiting smaller, longer-lived stars might become increasingly important venues for life's development. The biological future could be vastly longer than its past. Information processing, a defining characteristic of life and especially technological civilization, faces physical constraints in an aging universe. Theorist Freeman Dyson calculated that an advanced civilization could continue computing indefinitely in an expanding universe by strategically utilizing available energy as temperatures approach absolute zero. Such a civilization would need to compute progressively more slowly as energy becomes scarce, but could theoretically perform infinite computations over infinite time. This computational perspective suggests something profound. The universe's capacity for hosting intelligence and consciousness may have barely begun to be realized. While energetic processes like star formation have declined from their early peaks, information processing could continue for trillions of years, potentially allowing for more conscious experience in the universe's future than in its entire history. To date, human civilization, having existed for only about 12,000 years, represents less than 1/1,000,000th of 1% of cosmic history. Our technological development, spanning just a few centuries, occupies an even smaller fraction. Yet we've already begun contemplating solar system colonization and interstellar exploration, the earliest steps toward potentially spreading life and intelligence beyond Earth. If humanity or its successors survive long enough to establish a multi-planetary or interstellar presence, Earth might be remembered as not just our birthplace, but as an incubator for life's expansion throughout the galaxy. From this perspective, we may be witnessing not just Earth's biological story, but the very earliest moments of cosmic biology, a process that could continue long after our sun exhausts its fuel and our home planet becomes uninhabitable. This biological context reframes our original question. Rather than asking whether the universe is young or old, we might better ask whether its capacity for complexity, life, and intelligence has been mostly expressed or largely remains untapped. As we reach the conclusion of our cosmic journey, we confront what might be called the perspective paradox in determining the universe's life stage. Every metric we've examined yields a different answer, suggesting our universe simultaneously occupies multiple ages depending on how we frame the question. Chronologically, at 13.8 billion years old, our universe has moved well beyond its infancy. Star formation peaked roughly 10 billion years ago, and the most massive, brightest stars from the early universe have long since perished in spectacular supernovae. The cosmic microwave background has cooled from thousands of degrees to a mere 2.7 Kelvin. Galaxy formation has transitioned from the chaotic mergers of cosmic noon to the more stable structures we observe today. By these measures, we inhabit a mature universe approaching middle age. Yet when measured against projected future timescales, we appear remarkably early in cosmic history. If the universe continues accelerating under dark energy's influence, stars will continue forming for perhaps 100 trillion years before raw materials are exhausted. Red dwarf stars born today might shine for up to 10 trillion years. Even after the last stars fade, proton decay and black hole evaporation will unfold over timescales measured in 10 to the power of 100 years or longer. Against this vast future, our 14-billion-year-old universe represents the barest beginning of its potential existence. This temporal asymmetry, a universe whose most energetic days lie in the past, but whose total duration stretches far into the future, creates our paradox. We inhabit what might be called the stelliferous era, when stars still shine and complex chemistry remains possible. This era, though long by human standards, represents just a brief habitable window in cosmic evolution. Perhaps most remarkably, we find ourselves positioned at a unique observational moment. We can still detect the cosmic microwave background, radiation, still observe distant galaxies before they accelerate beyond our light horizon, and still infer the Big Bang through multiple independent lines of evidence. Future civilizations emerging tens of trillions of years from now would inhabit a darker, emptier cosmos where such observations would be impossible. They might never know the universe had a beginning or contains anything beyond their isolated galaxy. This fortunate timing mirrors another perspective puzzle. The Copernican principle suggests humans should not occupy a privileged place in the universe, yet we appear to exist during a rare window when comprehensive cosmic understanding remains possible. This seeming coincidence might be explained by the anthropic principle, the observation that regardless of how brief this window might be, intelligent observers must necessarily find themselves within it. Our biological timing adds another layer to this paradox. Complex life emerged on Earth after nearly 10 billion years of cosmic evolution, time required for multiple generations of stars to forge the necessary heavy elements and for planetary systems to stabilize. Yet viewed against potential future biospheres around longer-lived stars, Earth's biosphere may represent just the beginning of the universe's capacity to generate complexity. The development of science and cosmology on Earth has allowed humans to reconstruct the universe's history and project its future, achievements that would have been impossible in the early universe and may become impossible again in the far future. This suggests we occupy what might be called the universe's self-awareness phase, when it contains conscious entities capable of comprehending its nature and evolution. If we frame cosmic age in terms of consciousness and understanding, rather than mere chronology, we might propose that the universe is precisely as old as it needs to be for self-reflection to have emerged. In this sense, the 14 billion years leading to this moment represent a necessary prelude to the universe, becoming conscious of itself through minds like ours, neither too young nor too old, but precisely the right age for cosmic comprehension. This framing suggests a compelling answer to our original question. We inhabit neither a young universe nor a dying one, but rather a universe in its prime, mature enough to have developed complexity, yet energetic enough to sustain it for eons to come. We exist at the sweet spot between cosmic infancy and senescence, when stars still shine, planets still form, and minds still have time to understand the magnificent cosmic story that brought them into being. As we gaze both backward toward the Big Bang and forward toward the Big Freeze, we recognize our privilege in occupying this remarkable moment, the adolescence of awareness in a universe that has only begun to know itself. Whether this cosmic awakening represents a brief anomaly, or the first moments of an extended epoch of consciousness remains, like so much in cosmology, a question for future explorers to investigate.